All right, we're going to do another sample problem, 1431 from the end of the chapter of your textbook. This one involves calculation of Kc from data related to the Kp, okay? What these are equilibrium constants. You may have forgotten from the lecture, but there's two sort of types, if you will, of equilibrium constant. They really give us the same information, that is, where an equilibrium lies, but one is defined in terms of molarities or concentrations, hence the C. The other one is defined in terms of partial pressures, hence the P. So for any equilibrium reaction, such as this generic form, where the lowercase letters are the stoichiometric coefficients in the balanced chemical equation, and the uppercase letters are the reactants and the products, I could define my Kc in concentrations or molarities as the concentration of the product raised to the stoichiometric coefficients in the balanced chemical equation divided by the product of the concentrations of the reactants raised to their stoichiometric coefficients, lowercase a and b. Similarly, I could use partial pressures instead of molarities, and then I'd have a Kp expression. It's important to realize that Kp and Kc are not the same number. They're not equivalent. And because of that, sometimes we need to convert between the two numbers. This problem basically shows how to go about doing that. So we're to calculate Kc from a Kp value for this reaction. It's for the dissociation of molecular iodine into two copies of atomic iodine. We're given the Kp, 6.26 times 10 to the minus 22nd at 298. Boy, that's a really small Kp, so that tells me that this is very, very, very reactant heavy. In other words, this stuff does just not break apart just by itself at room temperature. And we recognize that because iodine's very much a molecular diatomic and at room temperature. You have to do a little bit of work to get it to break apart, okay? And there's a couple different ways you could do that, but at room temperature it just doesn't generally fall apart by itself, at least indicates that it doesn't do that according to the K. Now, if we need to convert between the two, we need to use this equation. This is the key to help us do that. The equation says that Kp is equal to Kc times RT raised to the power delta N. Okay, now what are all these terms? Well, Kp and Kc we already talked about. Those just our equilibrium constants. One's for concentration, the other's for pressure. R is going to be our gas constant. T is going to be our Kelvin temperature. And delta N, superscript here, is the change in the number of moles of gas phase materials over the course of the reaction. Finding delta N is, generally speaking, the most challenging or tricky part of these types of problems, but as we'll see, it doesn't really need to be considered all that tricky. It's something that each and every one of you can handle once we understand where that comes from, okay? So let's start plugging in numbers that we know to solve towards what we want to know. Now, we're told the Kp, we're given that in the problem. It's 6.26 times 10 to the minus 22nd. Okay. We don't know the Kc. That's our unknown variable. So what do we know about R and about T? Well, of course, R is our gas constant. It has a value of 0.082. And I usually truncate that to 82, but I'll continue it on here, 0.08206, okay? This is the one we usually use for pressures. The other number, the 8.3145, has got energy units attached. So when you're doing an energy calculation, activation energy, for instance, you use that one. But this is sort of the one that's associated with atmospheres or pressures. Okay, so moving forward then, we need our temperature. That's going to be our 298 Kelvin. We're specified that here in the problem. We're told that that's the Kp value. If you change the temperature, remember K changes. So usually these problems specify the temperature. Now we're going to multiply these numbers together, but we also need to raise it to the power of delta N. We got to find that term, okay? The change in the number of moles of gas. So let me do some erasing here so I don't run things together. And then let's talk about how to find that delta N term, okay? How do we find the delta N? Well, generally in chemistry, when you're computing delta something, it's the change in some variable. Here it's the change in number of moles of gas over the course of the reaction as read from left to right. So that basically then breaks down into taking a final measurement and subtracting an initial value. And that defines the change, final minus initial, final minus initial. And I remember this when I'm computing delta N because it helps me, okay? Sometimes it's confusing to figure out, which number of moles go first, reactants or products, as we'll see, okay? But if I remember final minus initial, that helps me a lot, all right? Now, what do I mean by this? Final minus initial, the change in the number of moles of gas that over the course of a reaction. Well, if we were to add up all the number of moles of gas on either side of our arrow, that represents the total number of moles in each condition, okay? So if I'm doing final minus initial, I need to add up the total number of moles as my products and subtract the total number of gaseous moles of reactants. So total number of gaseous moles of products minus total number of gaseous moles of reactants. Now in this particular example, my products feature 2 moles of gaseous products. Now, if I had some other gaseous products, I'd have to add those in. It's the total number of moles of gases on the right side minus the total number of moles of gas phase materials on the left side. Now here that's only 1, because I've got 1 mole of I2 as written, okay? So my final minus initial is 2 minus 1, and here my delta N is equal to 1, okay? So over here, I raise that to the first power, which basically means that that term appears in the mathematics, okay? So now that I've computed delta N successfully, I can go ahead and do my math. If I do that, and I multiply these two numbers, that product is a little over 24, 24.4538. Multiplied times Kc is equal to my Kp, 6.26, times 10 to the minus 22. Now all I need to do is solve for Kc through division. If I do that, take this, divide it by this 24.45, end up getting 2.56 times 10 to the minus 23rd. And that's the value for the Kc for this reaction. So I simply did a conversion between the two. The rest of the problems for this particular example work essentially the same, so I'm not going to work those. There might be a difference in the delta N, but we'll let you figure them out and check your answers at the back of the book.